Good morning, everyone. My name is Charity. I am a student teacher at for UBC MCAT, and I am also studying at UBC. So today we are going to continue on with organic chemistry alkenes. So last time we stopped at understanding how you can generate alkenes from in the classroom, and today we will be going on and moving on to alkene reactions. So a lot of the reactions we talk about alkenes actually happen um, on the double bond, and that's why alkenes are so much more reactive than alkanes. Because in alkanes, remember, we only had a few reactions, for example, combustion, but in alkenes, we'll have a lot of addition reactions, and you will see these reactions later on. These reactions will include chlorine, bromine, hydrogen, hydrogen halides, and ethene, and more, right? So we're going to move on to alkene combustion reactions today. So alkenes, unlike alkanes, which burn blue, alkenes burn yellow. So alkenes with the double bond, they will burn yellow and they will have a sooty and smoky flame. And so this is an important thing to know because sometimes you'll be asked for like a test. How do you know what, like you have a big liquid, let's say you have a bunch of liquid hydrocarbons. How do you know if that's an alkene or an alkane? Well, you can do a confirmatory test for a double bond, a C-C double bond, right? And if it burns blue, then you know it's an alkene. If it burns yellow and it's sooty and smoky, then you know it's an alkene. So this is a very good test that you can use. So this is the alkene combustion reaction in excess air, right? So here you can see in excess air. Oh, in excess air, the alkene is added to oxygen in gas state, and then it produces carbon dioxide in gas state and water in a gas state. However, if it's in an area of limited air, you notice that it doesn't produce carbon dioxide. It produces carbon monoxide, so it only has one O in the carbon output. And so obviously these two reactions, the excess air reaction and the limited air reaction, they are not balanced. So let's look at some examples to see how we can balance them. So first we have these two questions. Please take the time and pause the video now to try this out yourself. All right, I'm pausing the video now. We will take a look at the first question. A mixture of butane and butene can be separated by fractional distillation. How will you be able to differentiate the two compounds through fractional distillation? So does anyone recall what fractional distillation is? That's right. Fractional distillation is when you have a mixture of hydrocarbons. It contains alkanes, it contains alkenes, and it contains different lengths. So you have different lengths. And so if you heat it up, because they are different, the hydrocarbons have different properties. For example, butane and butene have different boiling points. They will be able to be separated and boil and turn into steam at different points inside the fractional distillation tower. So what we will be able to do is we know that butane has a lower boiling point than butene, right? Because it doesn't have the double bond, so it boils faster. So it becomes steam faster, so it will travel up the fractional distillation tower higher, and then you will find it in the tower higher than butene. And then part B, suppose you have two samples, one of butane and one of butene, but you don't know which one is which. What is a confirmation test you can perform on the sample to verify? Answer, you can burn a small sample of the fuel. Alkanes should burn blue and alkenes should burn yellow. You can also compare boiling point, like we said earlier, but it's also a bit difficult because they do boil at very high temperatures. So if you just have two samples, it'd be hard for you to perform on the samples. Melting point also works in that term, but it also requires extreme temperatures, right? Because yeah, we usually for like ease, you might just want to burn a small sample of the fuel and watch the color. When you're looking at viscosity and solubility, they will not work because even though they are different compounds, the properties of viscosity and solubility are very similar between the two, and it's very hard to tell. So it's not a very good confirmatory test. So continuing on with combustion reactions. A fuel-powered car uses a combustion chamber to ignite the fuel on fire and create force to accelerate the vehicle. The reaction in the combustion chamber is a combustion reaction. Suppose a car only has pentane for fuel. What is produced in the exhaust tank? And then part B, what if the car uses pentane for fuel? What is produced in the exhaust tank? And then C, is it better to use pentane or pentene for fuel? Why? Please pause the video now and answer the questions. Unpausing the video now, let's take a look at the first question. The car has only pentane for fuel. So what should be produced in the exhaust tank is CO2 and H2O, which are the common products of combustion reactions. And you notice that when we use pentane for fuel, it is also produced CO2 and H2O. And you notice that it actually doesn't change whether you use alkane for fuel or pentane for fuel. However, it is better to use pentane. And the answer is because alkene hydrocarbons do not occur naturally and are manufactured through cracking. So not only do you have to do extra steps to create fuel, it's also less efficient because when you burn alkenes, they actually produce unburned carbon, such as soot, and because it is a sooty flame. But alkanes will burn very pure. So it's always better to use, not always, but most of the time it's better to use the alkane instead. Here is another question. A fuel-powered car is put inside a small enclosed garage room. And you want to notice that this is an enclosed garage room. So what can we do in this case? With the garage door closed, inside the room, the driver turns on the car engine. Using this information, please answer the following questions. Unpausing the video now, let's take a look at part A. Suppose the car inside the room is only using pentane for fuel. What is the chemical equation in the car combustion chamber? So what is the combustion chamber? The combustion chamber is basically the car engine. Inside the car engine, the car will produce a combustion reaction using the alkene or the alkane that is using for fuel and actually do perform the combustion reaction. So if you look, here's the balanced equation. So we have pentane, which if you follow the formula is CnH 2n plus 2. So over here we have C5 and then H2n plus 2. So 5 times 2 plus 2 is 12. So that is our alkane formula. And then we look at, we write what the first step should be. You write out the alkane, then you write out the O2, and then you write out the CO, and then you write out the H2O. So why did we choose CO instead of CO2? Because we are in a small enclosed garage room. That tells you that we are not able to have excess oxygen. We are inside a limited space. And so that actually causes us to produce CO instead of CO2. So now that we have our products and our reactions, then we can start balancing the equation. And so once you do the math, this is the completed balanced equation. Next, we're asking, what if the car used pentane for fuel? What is the chemical equation in the car's combustion chamber? So again, we should write out the formula for pentane. And the formula for any alkene with the double bond alkene is CnH2n. And so obviously that becomes C5 is H2 times 5 is 10. Then we write out the O2, the CO, and the H2O, and then we calculate the coefficients, the 10, 10, 10, 2, and then we balance the equation, and then we are complete. So last of all, we have a question. So this is not actually a chemistry chemistry. This is a biology question, but it's something important to know for you guys. So what is the effects of CO on your body? In your body, there are hemoglobin blood cells, and so the CO is actually recognized as similar to CO2 and can cause death because your blood cells will start carrying the CO instead of the CO2. And then that actually causes your body to build up with CO and it causes a bunch of other issues. So it's not very good because it can cause death. Continuing on with our reactions. So we have done now combustion reactions and we will go on to addition reactions. So the definition of an addition reaction is found here. So an addition reaction is one where an unsaturated compound reacts to form a saturated compound. So does anyone remember what unsaturated compound and saturated compounds mean? Please take the time here and answer yourself. I'm pausing the video now. Unsaturated compounds are things that have double or triple bonds. For example, this ethene here is unsaturated. And a saturated compound means it is saturated, means it is filled with hydrogens. So every single carbon is filled with as many hydrogens as it can hold. So this one, technically you could add more hydrogens to it because carbons can have up to 4 bonds, right? So technically you could remove this bond and attach hydrogens. So this ethane is saturated. So ethene with a double bond is unsaturated. So addition reaction. So we turn an unsaturated compound to a saturated compound where it has no double bonds or no triple bonds. And we can do that through a variety of reactions. So what are we using to add to make it saturated? You can add a chlorine molecule to ethene. You can add a bromine molecule. Over here, if you turn it into ethane, you can add hydrogen. You can add hydrogen halides. You can add another ethene to it. And so adding these different types of atoms or molecules chemists call them different reactions. So we're going to look at some of these different reactions, and these are just the reaction names. So first we have the reaction hydrogenation. So this is when hydrogen in the presence of palladium or a nickel catalyst at a very high temperature will react with alkene to form alkanes. So this is sort of the general formula. So you notice that the formula actually doesn't use palladium or nickel. And that's because palladium or nickel is a catalyst and it actually isn't used. So a catalyst is not used in the reaction, but it is important for the reaction to happen. So we'll take a look at that for now. So over here you can see that, hey, we have the alkene and we have the hydrogen. So we're actually adding, so this right now, our alkene is unsaturated. It is unsaturated because look, the carbon can technically be attached to more things. So what we'll do is we'll take this electron and we'll combine it with this electron. And we'll take this electron and we'll connect it to this electron. And so then we can look at the final reaction. So here you can see that we start with an ethene, for example, and then we add our hydrogen, right? We found our hydrogen here. And then we will get to, using a nickel catalyst, we will get to our saturated alkane. So here's what actually happens. The metal catalyst is actually holding the hydrogens because otherwise it's very hard to break H2 apart. So the metal catalyst actually holds the hydrogens, so then ethene will come around and then attach to the hydrogens and leave. And so that's why nothing happens to the metal catalyst, but it's important to be used in the reaction, right? If it doesn't have the metal catalyst, it's very hard to do a hydrogenation reaction. So that's just what's important for you guys to remember. So now we're going to look at a hydrogenation example. So please pause the video now and try out these two examples. Unpausing the video right now, let's take a look at the first example. What is the product after hex-2-ene is reacted with excess hydrogen in the presence of a catalyst? Let's take a look at the answer. So hex-2-ene means that at the second carbon, it would have had a double bond here. But obviously, once we remove the double bond, then we just add 2 extra hydrogens on the side. So it's very simple. It doesn't matter where the double bond is. It's going to look the same afterwards because it's all going to be saturated. So there's no difference between adding the 2 hydrogens here or adding 2 hydrogens here, right? Because depending on where your double bond is, you're just going to add 2 hydrogens and then it'll all look the same and you'll have an alkane. Next, we're going to answer the second question. This one's a bit harder. Let's go over it carefully. So when hydrogen gas is passed through liquid vegetable and animal oil at about 180 degrees Celsius in the presence of nickel catalyst, solid fat is formed. Explain why. So let's take a look at this for now. Liquid vegetable and animal oil, understandably, they are all liquid at 180 degrees Celsius. That is a very hot temperature, right? So vegetable oil is unsaturated, and animal oil is often saturated at room temperature, right? At room temperature, animal oil will kind of be solid, and at room temperature, vegetable oil will still be liquid. So now that we've turned them both into liquid at a very high temperature, suddenly we realize we're still getting solid fat. So let's take a look at the unsaturated vegetable oil and the saturated animal oil, right? So we can see there are two types of fatty acids, which is sort of what is actually a vegetable oil and an animal oil. So the animal oil is saturated. So you can see that it just zigzags in almost like a straight line, right? There are no curves. And if you see the liquid vegetable oil, if you can see, you have one curve. It's very big, right? It's not very straight in a straight line, right? And you can also see over here, it has multiple double bonds. And that causes it to curve. And so there's this bit of space here. And then over here, it's also like a bunch of space here. So what does that mean for the molecule? So when you have a lot of saturated fatty acids, you can imagine you can have a straight line, and then you have, on top of it, another straight line, and another straight line, and another straight line. It stacks it very easily, right? However, if you take a look at these two, they're not going to stack as easily, right? If you have like these unsaturated fatty acids, you're going to have like weird shapes, and it's not going to be very easy to stack, and it's going to make a lot of air bubbles, right? So explain why. We're going to take a look at what we know now, the answer. So first of all, we know already established vegetable oil is unsaturated. It has double or triple bonds on the carbon backbone, and animal oil is saturated. It only has single bonds. And we've taken a look at what this actually looks like in the chemistry format, right? We can see that the bonds actually make them easier to stack or hard to stack, right? Because they're in different strange shapes. So we noticed that something is strange. We're actually going to address something. Alkenes have a higher boiling point than alkanes, right? So that means vegetable oil should boil faster than animal oil, right? However, the double and triple bonds make it harder for the long fatty acid carbon chains to stack on top of each other, right? So hydrogenation means unsaturated becomes saturated vegetable oil. And so that the long carbon chains stack more easily and there are more London dispersion forces, right? So if we pass these two unsaturated fatty acids through a nickel catalyst, right, it will become saturated. For example, this one, right? It'll become a straight line. So then we will get rid of this double bond. 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 And then we just attach them to hydrogens. And then they will all be straight lines again, right? So that means that they can stack a lot easier. And that creates London dispersion forces, intermolecular forces between the molecules. And that means if they have stronger forces, it becomes more solid, right? Hydrogenation is thus used to harden oils to solid fast, especially margarine. So that's sometimes margarine is like a type of oil. It's a solid oil, but it doesn't contain animal fat. It's not butter, right? So that's usually like used. Sometimes you'll see that, oh, they've used vegetable oil and they've just used hydrogenation to turn them into turn them into saturated fatty acids. Now let's take a look at alkenes versus alkanes, right? So alkenes should have a higher boiling point at alkenes, right? But we all know that animal fat, for example, butter, at room temperature, it is solid, right? However, vegetable oil is liquid. But vegetable oil is an alkene, whereas animal oil is alkane. So why is animal oil a solid, whereas alkene, vegetable oil, is liquid? And that's because it's the double and triple bond. So over here, the answer should not look at boiling point at all. It should look at London dispersion forces and how easily the molecules stack on top of each other. So that is the answer for this hydrogenation example. Next, we're going to look at halogenation and reaction with halogen halides, right? So we're just going to use X. X is a molecule that doesn't exist on the periodic table. It's a hydrogen. We're just going to make it a halogen. So this is like a variable, for example. So it could be any of the following halogens: fluorine, chlorine, bromine, iodine. Let's take a look at halogenation first. So this is halogenation. So this is when you have an alkene, for example, ethene, and we're going to add X2, for example, chlorine 2. And then all we do is we take the double bond, we remove it, and then we add 2 chlorines. And that's all we have to do. And that's halogenation. It's as simple as hydrogenation, except what you're adding is not hydrogens, it's chlorides or fluorines or bromines or iodines. It's just a halogen. And that's why it's called halogenation. So you're generating a halogen onto your alkene through an addition reaction. And then we have hydrogen halide. So HX is a hydrogen halide because X is a halide and then H is a hydrogen, right? So this could be HCl, HF, HBr, HI. These are all hydrogen halides. So here you have the alkene. And then you have your hydrogen halide, HBr, and then you've turned it. So all you did, you removed the double bond and you added a Br and a hydrogen. So this is what you formed your bonds. You formed a C and a Br bond, and then you formed a C and a H bond, right? And then you broke the CC double bond and you broke the bond between the H and Br. In halogenation, where you're reacting with Cl2, the color of the halogen fades as the number of molecules of halogens remaining unreacted decreases or reduces. So this really means that a lot of times you'll see halogens like Cl2 or F2 show like a color. But as you're reacting this, you're breaking these bonds. You're turning them, you're attaching them to the alkenes and making them into alkanes, right? You're actually getting rid of the color, right? Even though the molecules do not disappear, the color disappears because this molecule no longer exists. It becomes a part of a different molecule. So the color fades, and that is what this means. So HX is the halide. Now we're going to take a look at a reaction with Br or Cl water, bromine water, or chlorine water. So we're going to take a look at formation of bromine water or chlorine water. So what is bromine water or chlorine water? So first we're going to take a look at these to answer to what bromine water or chlorine water is. First of all, bromine water is a halogen, or chlorine water is a halogen dissolved in distilled water. So this is bromine dissolved in distilled water or chlorine dissolved in distilled water. So, for example, this is chlorine water. So you have the OH, right? You can recognize this is from the water, and then you have it attached to a Cl instead of another H. So this is chlorine water. Then you have bromine water, which is the same thing, except it's attached to Br. And so they have different names too. This is called hypochlorous acid. This is called hydrobromic acid. It can also be called chlorine water or bromine water. We're just going to say chlorine water or bromine water. But you want to also know these terms as well. Hydrochlorous acid or hydrobromic acid. How do you know they are acids? Pause the video right now and answer the question. Unpausing the video right now, we know that they are acids because acids can donate hydrogens. So over here, you can see that even though it only has one hydrogen, it can still donate it because, right, these oxygens are stable, right? This oxygen, right, like they're the same type of oxygen where they have like 2 lone pairs and 2 connections. So that means they have 8 valence electrons. So they're stable and they can donate. They can lose the hydrogen here very easily. So they are acids, right? They cannot accept hydrogens. Even though it looks like an OH group, it can't take any more hydrogens because it already has 8 valence electrons. It's not going to accept more hydrogens, even if, right, because it has the bromine or the chlorine. It's not going to take more hydrogens, but it can give up its only hydrogen, right? So now we're going to look at the actual reaction. So this is an alkene reaction with Br or Cl water. So first, we're going to see the double bond breaks from the alkene, right? The alkene has a CC double bond, that's going to break. And then the Br or the Cl, so this is going to split off from the OH, right? So we're going to remove this from the OH. And then the Cl and Br each attach onto the CC double bond and make it a single bond, right? To the former bonded carbons. So here is our alkene, and here's our example, chlorine water. And we notice that this thing breaks, right? So OH goes onto one of the carbons, and then Cl goes onto the other one. So over here, this is not breaking the H bond. We're not being an acid-base reaction, right? This is not an acid-base reaction. This is just, we break the OH and the halogen bond, okay? So don't attach H and then OCl, because that's not what we're breaking here. We're attaching OH and Cl. Next, we have an oxidation reaction. So what is oxidation? Please pause the video right now and answer the question. Unpausing the video right now, we can see that oxidation, through this example, this is an acronym. So this is something that is good for you guys to remember. So you can say oil rig. So you can spell it out. Oxidation is loss of electrons. Reduction is gain of electrons, right? So what is an oxidizing agent? The molecule which takes in the electrons that are lost. So it is the, right, an oxidation reaction will always happen at the same time as a reduction reaction, because if you lose electrons, something has to gain those electrons, right? Then that's what makes it stable, right? So that's a redox reaction, right? So in a redox reaction, we will have an oxidizing reagent and a molecule that gets oxidized. So when the molecule that gets oxidized loses electrons, another molecule will gain those electrons, so it's the molecule that gets reduced. So here is an oxidation reaction. Here you have molecule A, it loses electrons. And then molecule B is your oxidizing reagent, because this loss of electron will go into B. B will gain electrons. So we will now watch this video talking about alkene oxidation and alkene reduction. I have linked the video inside the YouTube video like description. Please watch the video until around minute 8. You don't have to learn about alkene reduction. It's useful, but I don't think it's needed yet. Please ask your teacher if they have changed the KCSE, but I don't think it's going to be tested on the KCSE. Unpausing the video right now. Welcome back from the video. I hope you learned about alkene oxidation. So we're going to talk about the alkene oxidation. So here we have alkene plus an oxidizing agent, and it becomes alkenyl with a dual or double functional group. So these are some of the common oxidization agents. So you can have orange acidified potassium or sodium dichromate. So this does not mean potassium and sodium dichromate. It means potassium dichromate or sodium dichromate solution. So this is dichromate CR2O7 is dichromate. And then you have your potassium or your sodium in front of it, right? So it starts as orange, and you notice that if you add it, it turns green, right? After the reaction of the alkene. Then you have acidified potassium or sodium manganate solution. So this is purple. So after you react with an alkene, it will turn into no colors. It will be colorless, basically, like water. So it doesn't have any color after you react with an alkene. So an example, here you have an alkene. This is propene, so it has 3 carbons and 1 double bond. And you're adding that to potassium manganate solution. And then these are on top of the arrow are other factors in the inside the solution, but you don't need to use any of that in your final products. You just have your reactants and your products, and these are, let's say, catalysts or conditions for the reactions, right? So you notice that here we actually produce 1,2 propanediol, right? So we have 2 OH groups right here. Now we're going to move on to hydrolysis. So hydro means water, right? It's just very common to use hydro as water, and then loss is lysis. So here we are losing water. So what does that mean for the reaction, right? Hydrolysis is the reaction that uses up water, because water is used, water's in the reactants. You're taking up water, there's less water around the other place because the water has been used and put into the reaction. So alkene hydrolysis reaction means an alkene plus a water becoming an alkenol. So this is an alkane plus an OH group, right? So this is an alcohol, an alkane alcohol, right? Here you have your alkene with a double bond, your alkene with a double bond, and here you have your alkane or the alcohol, right? So here you've split the H and OH group and you've added H to one side and OH to the other side. This is very simple, right? Like we just break the double bond and then we form the reactants with new water. Here is actually what happens through alkene plus water becoming the alkenol. So this is just for example. It is good to know, but you please ask your teacher if you need to know every step. This is just good to know of what actually happens through the reaction. So what actually happens in the reaction is you have like a very strong acid. For example, you have H2SO4. This is the formula, and this is like the Lewis structure. So this is the formula H2SO4, and this is how H2SO4 actually looks, right? And then you have your alkene. This is very simple. We've already seen alkenes before. So now we're gonna inside this reaction, this will require a very strong acid. And so in this case, we have H2SO4, which is a very strong acid. So this double bond is actually 2 electrons, right? There's an electron on this end, on one end of the double bond, and there's an electron on this end of the double bond. So these 2 electrons will go and attack this hydrogen. And then this bond will break, and these 2 electrons on this double bond will jump on as a lone pair onto the oxygen. All right, let me repeat that again. This bond has 2 electrons. It goes and attaches to this hydrogen, this single hydrogen with no, so this is 1 proton, basically. 1 proton is 1 hydrogen, right? Because in this case, the 1 electron in this hydrogen is in this bond. And so this bond actually goes back to the oxygen. So this bond, this hydrogen is not taking any electrons with it. It's just taking the single proton. And so what we end up is we have this bond over here, and we have the hydrogen, the proton, and then we have the lone pair moving on here, so there's now a negative charge. So you notice that we've actually stolen an electron from this carbon. This electron has moved to the hydrogen. So now the hydrogen is balanced, and this carbon is still balanced, right? But then this one has a positive charge. We have a positive charge and a negative charge. And then we also have water. So water also has a lone pair over here. So lone pair on water will be, because the lone pair is electrons, so electrons are negative, right? So it'll go to this carbon and attach itself onto the carbon. So now we have the carbons are both balanced, but this oxygen is no longer balanced. This water on the oxygen on the water is no longer balanced. However, we still have a negative charge, right? So what we're going to do is actually this thing is going to negatively attract to the hydrogen, and it's going to attack it, right? Because this is positively charged, right? Because we have like the positive charge is because it has the lone pair, right? Because it wants like 6. So if you count it, it has 1, 2, 3, 4, 5, 6 on 5 on or surrounding the oxygen, because the other 1, 2, 3 on the other side of the bonds are actually being shared with the other ones. So that's why it has a positive charge. Even though technically its valence electrons are met, it will still have a positive charge. So because it has a positive charge and this one has a negative charge, because this one has its valence electrons all met, but it has 1, 2, 3, 4, 5, 6, 7 of the electrons surrounding it, it will attack the hydrogen, and then that will give us the final answer over here. That will give us, we've removed the hydrogen off this one, right? And the double bond has broken off and jumped back onto the water or the OH group as a lone pair. So now everything is happy. Everyone is happy. No charges. No, all the valence electrons are full, right? And we also have what we started with, right? So if we added a hydrogen onto this thing, then we have what we began with, like H2SO4. So looking at the steps, we have step 1, step 2, step 3, step 4. We're going to condense some of the steps, possibly. So first we have the alkane and a concentrated sulfuric acid solution. And that becomes our alkyl hydrogen sulfate. Then step 2, 3, and 4, what we actually do is we add warm water and we make it into an alkanol. So this is our alkanol. So step 1, and you just really need to know step 1 and step 2, 3, and 4. So because all of this little changing of the charges, you don't need to write that here, right? Because you can just say we add water and it becomes, if you add water to it, it becomes OH, right? So you just need to know that before we do that, we need to produce this positive charge. Otherwise, water will not attack this carbon and this bond will not happen. The OH group will not get attached to it. So because this is very strong acid, this is very reactive molecule, this will actually remove the double bond for the water molecule to come in. So the water molecule will usually not come in to attack the double bond itself because water is very stable, right? So it's not going to come in and attack the double bond. So the reason why we have to do this convoluted method of using, this complicated method of using like sulfuric acid is because water is too stable. It won't actually create a reaction. So we add a very reactive sulfuric acid to make that positively charged so that it can actually go through with the reaction, right? So this reaction, technically, because we produce concentrated sulfuric acid at the end again, it's a catalyst. So that's why we don't really write it in the reaction, right? So on the previous page, you can see that we actually just say alkene plus water is alkanol, right? Over here, we have another very strong hydrogen, CH3O plus, right? Sometimes we'll use CH3O plus instead of H2SO4. But regardless, the reason why we have a catalyst is because water is too stable. It won't actually attack the double bond. So what we do is we do this complicated thing to make it so that it has a positive charge and then water will actually want to go towards the carbon. So, because it's a warm water, it will provide some heat to finish the reaction. So here is our second one. So we have step 1, right? So we have the H3O plus, and then we have the alkene with the double bond. So we have our catalyst, H3O plus, and then we have the alkene, which is ethene. So again, we have this very reactive agent. We're trying to get it so that the alkene has now a positive charge, right? So then water can attack it, because that's when the stable water will actually want to attack the carbon, the hydrocarbon, right? And so then step 2 and 3, we basically combine that, right? So that becomes we get an alkene to an ethanol. So here, we don't have to use alkyl hydrogen sulfate or our sulfuric acid, because we have a different very reactive agent, right? So it doesn't really matter. It doesn't really matter what we're using as our highly reactive agent here. It just matters that something makes this alkene less stable so that water will actually attack it, right? Now we're moving on to the final step. So this is a polymerization self-addition reaction. Polymerization is actually really, really, really important because this is a lot of how materials you guys use in daily life is actually made. And this is why chemistry is important, because if we understand alkanes, alkenes, and alkynes, then we can make cooler molecules, bigger molecules that humans can use. So we're going to go through alkene polymerization. So this is when a small unsaturated monomer, the monomer, such as an alkene, molecule joins together to form a large saturated molecule. Again, we have unsaturated becoming saturated. So what this means is that we'll have many, many small alkenes joining together in like a list. So you have one alkene and then you add a second one and then you add a third one and then you add a fourth one, right? To form a large unsaturated molecule. Let's take a look. Only alkenes undergo addition polymerization. So alkanes will not. Triple bonds, alkynes will not. Only alkene double bonds will undergo this. So this is why this is super important, right? polar names will just be poly in front of the monomer. That's very simple. So here's our addition polymerization procedure. So first, many molecules are put under high pressure. So you have lots of alkenes put under high pressure. And then the double bond breaks to become a single bond. And remember, the double bond contains electrons, right? So when it breaks, it'll produce electrons and it'll become a free radical. That means it's electron as not a lone pair, but it's just a single electron floating beside that nucleus. And then what happens is the free radicals will collide with each other and join to form another molecule. Because it's not stable, right? The free molecule. So it'll collide with each other and become a line of bonds. Let's take a look at our first reaction. So we have ethene, and that's going to become polyethene. So here we have an ethene molecule, right? Have an ethene molecule, we break the double bond, right? We're going to break one of the bonds, and that's going to produce electrons, right? The free radical. This is a single electron, our free radical. Same thing happens to the other one. We break that bond, we produce a free radical. So then what we're going to do is actually join this bond. So this one, this free radical plus this free radical are going to be joined. So we notice that we actually make a bigger molecule, right? And so here we can see that if this happens many, many, many times for many, many different molecules, we can have N ethene molecules, and that becomes a chain of polyethene. Let's take a look. Formation of polyethene. So the commercial name is also polyethene. And so what the commercial name means is that the commercial name is what like most people will commonly call it as, because sometimes, you know, like the polyethene name is too long, or like the polymer name was too long or like too complicated. Like let's say there's like double bonds in like multiple places, or it's like a longer chain, right? Like people aren't gonna say like a very long name, so they'll just call it a shorter name, right? So it has a couple properties, and so it is elastic, it is tough, it is transparent, and it's durable, and it's plastic, of course, because this is what is known. Like plastic is a lot of these like hydrocarbon polymers. So a lot of plastic you use, they are polymers of some sort of like monomer alkene, right? So it is used in making plastic bags, bowls and plastic bags, and packaging materials. So all these things, polyethene, this is what you're using as. Next, we have another one. We have chloroethene, right? So this is where, like, this is also a 2-carbon hydrocarbon, but instead of all 4 of its substituents being hydrogens, we have a chlorine. So here, you see the same thing. We have a chlorine and we have a chlorine. And you get rid of the double bond. We have the free radicals, right? And then we combine the free radicals to join to be a bond. And so we, again, here's our formula. This is what it looks like. If you have N chloroethane molecules, you can join it to become a polychloroethane. So formation of polychloroethane, right? So the commercial name is polyvinyl chloride, PVC. And you can see, again, polyvinyl chloride, PVC. Properties, it is tough, it is non-transparent, it's a durable plastic. So this also gives different uses. So it is useful in making plastic rope. It's useful in making water pipes, crates and boxes, right? So all these things, PVC, polychloroethane, or polyvinyl chloride, that's very useful. Again, moving on, we have a different monomer. So this time, it's phenolethene. So we can see that this ring structure is called benzene, or it's also called phenol if it's in front of as a branch, right? So it contains 6 carbons. So if you count 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons, and it's attached to 5 hydrogens because this last carbon is attached to this main chain, right? And so what's special about it is just because it has like the circle inside actually represents like the extra electrons are actually being shared between all 6 of the carbons. So that's a very special one because yeah, it's just it's so stable. So that's why we named it, we gave it a special name. Like in this case, as a branch, it's called phenol, right? So here we have I didn't draw it out. I just wrote C6H5. So if you break this bond, again, you have the free radicals, right? And then the free radicals will join together and connect, right? And so then this is what it is. If you have N phenylethene molecules, you can have a polystyrene of N. So this is actually polyphenylethene, but the commercial name is polystyrene because this is a lot longer, right? So aka styrofoam. It's also known as styrofoam. So here are some of the properties. It's light, it's durable, and it's plastic, right? And uses in making packaging materials for carrying delicate items, ceiling tiles, clothes lining, all sorts of uses, right? Then we have another one. Here we have propene. So propene is actually not ethene, right? But we only have one double bond, right? So the other one basically looks like a branch. So even though it's technically like a chain of 3 carbons, we don't really need to worry about the CH3 at the end because all we're looking at is the double bond, right? So here we look at we ignore this CH3. We just look at the double bond. We break the double bond, we still get the free radicals. And we combine to join together. You get polypropene. Polypropene. Commercial name, polypropylene, PP, sometimes known. And then properties, semi-rigid, translucent, tough plastic, right? And then you have uses. Plastic packaging, plastic parts for machinery and equipments, fibers, and textiles. So these are sort of, this is polypropylene. Next, you have a very unique one. It is 2 carbons and 4 fluorines. So this is called, we know it's ethene, right? But it's got 1,1,2,2 tetrafluorine ethene. Tetrafluoroethene, right? So that's a very long name, right? So obviously we're going to give it a different commercial name, but the same sort of like polymerization logic happens, right? You break the double bond, you produce free radicals, you combine the two free radicals together to form another bond, and then you have, your formula here. So formation of polytetrafluorine, right? So this is a tetra because it has 4 fluorine molecules instead of hydrogen. Fluoroethene. Commercial name is Teflon, PTFE. Teflon is known very commonly, and it's tough, it's non-transparent, it's durable, right? It's got uses in making plastic rope, water pipes, crates and boxes. Next, we have another molecule, formation of rubber from latex. So this is different. So this is like something you don't have to know the exact formation, but it follows it because it's another polymerization. So it's very similar. So the natural rubber is obtained from a rubber tree. So rubber has lots of uses, right? And an incision is made on the rubber tree to produce latex. And then latex is added to an acid to coagulate the rubber. That means to harden it, right? So latex is a milky white mixture of rubber and water, right? And then natural rubber is a polymer of 2-methylbute-1,3-diene. So this is 2-methylbute-1,3-diene right here. You can see that we have a butene, right? A butene 1, 2, 3, 4. So that is our main carbon bond. But over here, we notice that obviously this is like the actual polymer. So this is natural rubber. But you can see that inside there's a monomer. You can see the monomer pattern here. And you can see the branching, the 2-methyl at the second point, and you can see the 2 double bonds. So there's one double bond here, and then there was another double bond here. Combining, like breaking like that, we will break that double bond to produce our polymer. So we have properties of rubber. It's soft, it's sticky, and has uses, erasers, car tires. And a lot of times, it'll actually undergo the process of vulcanization. So it's the process of heating rubber with sulfur to make it harder or tougher. So vulcanized rubber can be used in tires and shoes and all sorts of other valves and things like that. And it's quite useful, actually. So then we have another type. So we have another type. So this is 2-chlorobutyl-1,3-diene. This is very similar to what we just seen, except the monomer was, we had a 2-methyl group instead of a 2-chloro group. So here, all we did was change the methyl group to the chloro group. And so this is very similar to natural rubber, but this is actually synthetic rubber. So this is synthetic rubber because we have this chlorine group instead of the methyl group in natural rubber. So from a monomer of 2-chlorobutene-1,3-diene. So synthetic rubber can resist oil, abrasion, and organic solvents, which natural rubber cannot. So it's useful in other ways. So this is just good things to know because these are actually really useful and you could really genuinely use them in real life. Finally, we're going to test for the presence of the CC double bond. And you can do that multiple ways, right? Like we earlier discussed today's lesson, you can use smoke, burning combustion. All unsaturated hydrocarbons with a carbon-carbon double or triple bond burn with a yellow or sooty flame, right? Oxidation by acidified KMnO4 or K2Cr2O7. You can also replace the K with sodium, Na, right? So manganate, KMnO4, is purple. So if you add that to alkene, what does it turn? It should turn to no colors. And K2Cr2O7, that is orange. But if you add it to an alkene, it will turn green, right? So bromine or chlorine water combined with these oxidization reagents will change color, right? It'll actually change color in the presence of a double or triple carbon-carbon bond. Finally, on the last slide, we have uses for alkenes. We've already seen that it can be used to manufacture plastic because it can be polymerized, which is super useful. But it can be also used in other things. So if you do hydrolysis of ethene, it's used in manufacture of ethanol because hydrolysis produces ethanol, right? Of ethene, it produces an ethanol because the alkene becomes an alcohol. So then in 3, it's used in ripening of fruits. Alkenes are actually super useful because to ripen a fruit, to make a fruit ripe, it actually releases a hydrocarbon as like a hormone or stimulant to make the fruit know that, oh, I should be ripening. I should be producing the molecules to make myself sweeter and softer, right? And it's also used in the manufacture of detergents. And so that's everything for alkenes. Alkenes are super useful and super applicable to everyday life. So it's really important that you know this not only for the KCSE, but also later on in any jobs you might do. That's all for today. Thank you for watching and have a great rest of your day.